Determine the convergence or divergence of the following integral. And if it converges, find what it converges to. So we know from 0 to 5 of x minus 4 over x dx. And clearly, this integral has an issue at 0, right? If we plug in 0 to our function, it's undefined. So we want to rewrite this as the limit as a approaches 0 of the integral from a to 5 of x minus 4 over x. Now, it's also probably in our best interest to simplify the integrand, write it as x over x minus 4 over x. One more small thing that's not a really big deal, but we should, it's a big enough deal that we should kind of take care of it. If we're between 0 and 5, we're definitely bigger than 0. So we're approaching 0 from the right. Okay, so now we're going to simplify a little bit more. So the limit as a approaches 0 from the right of the integral from a to 5. X over x is 1 minus 4 over x dx. And now we anti-differentiate. We get the limit as a approaches 0 from the right. The integral of 1 is x. The integral of 4 over x is minus 4 natural log of the absolute value of x from a to 5. Then we get the limit as a goes to 0 from the right of 5 minus 4 times natural log of the absolute value of 5 minus a minus 4 times the natural log of the absolute value of a. So what we need to think about is what's happening to this natural log as a goes to 0 from the right. And for the natural log, I would like dividing by 0. Okay, you know when you divide by 0, the fraction gets infinitely large, or maybe negatively infinitely large, depending on the sign. For the logarithm, it can always be kind of hard to remember. I find it easiest to remember if you just remember what the graph of the natural log looks like. So here is the graph of the natural log of x, which has an intercept at 1, 0. And notably, as the x values go to 0, the y values go to negative infinity. So this part here, that's going to go to negative infinity, which means this whole thing is going to diverge. So I would say this diverges. And really, I would leave it at that. Because sometimes things diverge and you don't know if they diverge to infinity or negative infinity. This one you could actually say, let's see, it's a negative, negative, negative. So this one is diverging to negative infinity. Right? You have 5 minus 4 natural log of 5 minus a, and then minus minus negative infinity, so plus negative infinity. So it diverges. You could say it diverges to negative infinity, but I don't think that's super important. Do stop me if you have questions. I'm just going to keep going. But I will definitely stop for questions. What's this eraser? I think I need some new erasers. These erasers are kind of gross. There's like the dry erase pen goop caked onto it. It's really, really lovely. Also, just I was one thing I wanted to ask you guys. I know that so yeah, you guys' tests are so your tests are Monday and Tuesday, so you definitely don't need to have office hours on Thursday. Yeah. All right. Let's see. Where are we at? Let's look at this next one. More integration. So let's look at the integral of natural log of x plus 3 divided by x times the natural log of x plus 1 dx. All right, so here we just want to find the antiderivative, right? That's all this is saying. And it definitely looks like it's a U substitution problem. I see something in parentheses that's often a good candidate for U. Let's see if it really is. So U is going to be the natural log of x plus 1. And then my du, the derivative natural log of x, is 1 over x dx. Great. I have that, right? There's my du. So then I can start rewriting things. This is going to be the integral of the du. The denominator is just u. What about the numerator? Well, here's the thing. We're going to do a back sub, but we want to make our job as easy as possible. Right? Most of the time, a lot of the time, when you do a back sub, you take this and you solve for x. And you say, okay, so you could do that. You don't want to do that here. If you did that, here's what would happen. You would say u minus 1 equals natural log of x, and then e to the u minus 1 equals e to the natural log of x. So that x equals e to the u minus 1. And then you can plug that in for natural log of x and then kind of undo all the work you just did. Right? And say, okay, then I've got the natural log of e to the u minus 1 plus 3, which is u minus 1 plus 3, which is u plus 2. That's fine, that works, but we did too much work. The much easier thing to do is say, hey, look, I'm trying to replace this natural log of x plus 3. I know that u is equal to the natural log of x plus 1, so it's not too far of a leap to say, well, u plus 2 equals the natural log of x plus 1 plus 2, which is exactly what we want. So try to make your life easier, right? You don't want to do more work than you need to. If something looks like what you've already got and you're doing a back sub, try to just modify this so you can make it look like what you need it to look like. That's going to be a u plus 2. And this is actually going to be very similar to the integral we just did, right? When we integrated x minus 4 over x, we broke it up into two fractions, then we divided each thing. Same kind of idea here. We're going to write this as the integral of u divided by u plus 2 divided by u. Then we're going to integrate, we're going to get u plus 2 natural log of the absolute value of u plus c this time because it's an indefinite integral, so we need the plus c. And then we replace u with natural log of x plus 1. So it's going to be the natural log of x plus 1, not the absolute value of x, right? It's just the natural log of x plus 2 times the natural log of the absolute value of the natural log of x plus 1 plus c. And that would be our answer. All right. What else? Let's take a look here. Let me also, I will say, so I imagine most of you are not finishing UC Davis, although some of you could be graduating. But for those of you that will be here next year, come by the AATC in fall quarter. We will be in person, which will be feeling kind of strange after having been not in person for a year and a quarter. But we will be on campus, or at least some of us will be on campus. I will be on campus. So come by and say hi. I'd love to get to meet any and all of you in person. Yeah. Let's see here. Let's look at this next one. This next one makes me wonder. I feel like this next one has something in it that I don't know if we actually did. But let's talk about it. So I want to find the integral of x squared plus, oh, this is a gnarly looking problem. X squared plus cosine of 3x quantity squared. And this pen does not seem like it's very easy to see. Let me do one thing, but I feel like I should definitely use a different pen. Maybe it's just me, but I feel like it's not easy. So here's what I've written. It's x squared plus cosine x quantity squared. So if we're going to do that, we're going to have to multiply it out. So that's going to be the integral of, so let's see, if I multiply this out, x squared is x to the 4th. And then I'm going to have a 2x squared cosine of 3x. And then I'm going to have a cosine squared of 3x. So I don't remember. I know I've done it in 21B, but I'm not sure if we've talked about in this class how to integrate cosine squared. Have we talked about that? Does anybody, do you guys know how to integrate cosine squared? Anybody? Yes, no, maybe so. Oh, sorry, the chat's way down there. Yeah, I don't think so either. Okay, yeah, that's kind of my impression too. Okay, I will point out, I don't think it's going to come up on your final, but just in case it would, the way you integrate something like this is by using a trig identity. Specifically, the trig identity that cosine squared of an angle. So cosine squared of theta is equal to 1/2 of 1 plus cosine of 2 theta. That's what you do when you have cosine squared, is you replace it with that, and then you can integrate that. I think this problem is probably not super. This problem is fine. It's just kind of a giant pain in the butt. So, but again, assuming we haven't seen that, I feel like we should do it. Let's instead do this. I think the real point of this problem was to do the middle part. Let's do this integral instead. Let's do the integral of 2x squared cosine of 3x dx. I really feel like that's the part that they really want us to do, which is definitely an integration by parts problem. We have a mixture of things, right? We have a power of x times a trig function. So we're going to use integration by parts. Now, we could do integration by parts the long way, but since we have x to a positive integer power, and either sine or cosine or e to the x, this is one of those cases where we can use the tabular method. And if your teacher gives you the opportunity to use the tabular method, you should take it. It is almost always, it's going to save you time. So we're going to pick that for u and that for our dv. Really, technically, dv has this part too, right? But okay. So we make a little table. So for the u part, we write down that, and then we take all the derivatives of u, or we keep taking derivatives of our u until we get to 0. So derivative of x squared is 4x, derivative of 4x is 4, derivative of 4 is 0. And then for dv, we take the antiderivative. So our first dv is cosine of 3x. The antiderivative of that is sine of 3x divided by 3, or 1/3 sine of 3x. The antiderivative of that is going to be negative 1/9 cosine x. So it's going to be 1/3 times negative cosine of 3x and then divided by another 3. So it's going to be negative 1/9 cosine of 3x. And then the antiderivative of that is going to be negative 1/27 sine of 3x. So be careful when it's a sine or a cosine, because, well, first of all, when you have a multiple of x, you're going to keep dividing by that coefficient of x each time you anti-differentiate. But more importantly, when you have a sine or a cosine, be careful with the antiderivatives. Right? The antiderivatives have the opposite plus or minus pattern as the derivatives, right? So the derivative of negative sine is negative cosine. The derivative of negative cosine is sine. The derivative of sine is cosine. The antiderivatives have the opposite signs. No, I think so. So someone asks a good question here. Could one say that as a general rule, when you're integrating something raised to a power where two variables are added, subtracted, we should FOIL it? I don't know if that makes sense, but for example, 3x plus x cubed squared. And I would say the answer depends. So I'll address that after we do this problem. But yes, I think that's a good question, and I'll talk about it in just a minute. Finish this one. I mean, really, we have to write this one out, right? So we know that it's always this plus minus plus pattern here. So it's going to be plus this times this minus this times this. That's going to give me a positive sign over all this. It's going to be a minus 4x times a negative 1/9 cosine of 3x plus 4 times negative 1/27 sine of 3x. And if you wanted to make it look nicer, you could write it as 2/3 x squared sine of 3x plus 4/9 x cosine of 3x minus 4/27 sine of 3x plus c. Okay, so again, if you have the opportunity to use the tabular method, you should. So a better question, one that we might have been able to tackle a little more easily, would have been something like this. So here are two examples of things you should multiply out. The integral, so the one that was asked, for example, the integral of 3x plus x cubed squared totally would multiply that, right? So it's just going to be, let's see, 3x quantity squared, so 9x squared, and then 2 times 3x times x cubed, and then x cubed squared. That one, right? I mean, I don't think we really need to, we could simplify this slightly more. It'd be 9x squared plus 6x to the 4th plus x to the 6th. And all of you can integrate that. I don't think I need to say more about it. Here's another example of one you would want to multiply out. I don't want it to be too terrible. Let's say it's x plus e to the 5x quantity squared. This one, if you multiply it out, it's going to be x squared plus 2x e to the 5x plus e to the 5x quantity squared, which is e to the 10x. And then for this one, you would have to break it. Well, so here's what you get. You get the integral of x squared is x cubed over 3. I'm going to leave this part alone for a minute. The integral of e to the 10x is e to the 10x divided by 10. And the integral of 2x e to the 5x is another instance of having to use integration by parts. You could use a table here, but it's literally a one-step integration by parts, so I don't know if you really have to use a table. So you know what? I will say, I do still like the table because if you don't use the tabular method, then you can, right? You can use the tabular method here because again, it's a positive integer power of x and an e to the something or a sine of something or a cosine of something. I should say specifically an e to the something times x, right? If it was like x squared, then it'd be a u substitution. Right? If this was 2x e to the x squared, it would be a u sub. What I would want to point out was if you do it the longer way, when you can use integration by parts, you still have to write out uv minus the integral of v du, and then still do the integral of v du. So I think even though it's only a one-step integration by parts, it's still worth using the tabular method. So my u is going to be 2x, the derivative of that is 2, the derivative of that is 0. My dv is e to the 5x, and then it's 1/5 e to the 5x, and then it's 1/25. So every time we anti-differentiate, we just divide by 5. So this is going to end up being x cubed over 3 plus e to the 10x over 10 plus this times this minus this times this. So plus 2/5 x e to the 5x minus 2/25 e to the 5x plus c. It's kind of a gnarly question, but not too out of this world. Okay, that said, there are some instances where you really not only don't want to multiply it out, can't reasonably multiply it out. I'm going to give you two examples. So let's say I asked you to find the integral of, I don't know, 4x plus 1 to the 39th power. Technically, is it possible to multiply that out? Yeah, technically it's possible. And if you did, you'd have 40 terms. 40? Yeah, I think 40 terms. Too many terms, right? It's multiplying this out would take you all day. Maybe. I don't know. It'll take a long time. It'll take probably at least an hour to really accurately multiply it all out. It's a giant pain in the butt. but there's something we can do. So if you have something that's raised to a power that seems like really any power bigger than 3, the intent of the problem probably isn't for you to multiply it out. Like if you had something cubed, okay, multiplying it out might still be an option, but after like something to the 4th, something to the 5th, whoever is writing that problem doesn't want you to multiply it out, which is why they should really make it a super big power so you can't multiply it out. I've had students on tests, like I gave them like something to the 7th power and one person multiplied it. I'm like, oh, come on. So the next time I made it to the 70th power so that nobody multiplied it out. But here the idea is to do a U substitution. So we're going to let U equal really the only thing that makes sense, 4x plus 1. And then du is going to be 4 dx. So 1/4 du equals dx. Okay, and that's kind of it. So then we're going to have the integral of, let's see, so 4x plus 1 becomes u. Sorry, I should deal with always deal with the dx first. Sorry. The dx becomes 1/4 du. And this becomes u to the 39th power. And then we integrate. We get 1/4 u to the 40th over 40 plus c, which is going to be then u is 4x plus 1. That's going to be 4x plus 1 to the 40th power divided by 4 times 40 is 160 plus c. So there's an example of when you definitely do not want to multiply that or cannot multiply it out. Another example of this. Where my good pens go? Left to be. I need to do some culling of the pens over here. You can use orange. See how this orange shows up. Does that say ux or 4x? Good question. That says 4x. Yeah, that's it. My 4's and my u's, unfortunately, kind of look the same. That's a 4x. Another example, something like, oh, that could be interesting. Let's not make it too terrible. The integral of, that seems like, yeah, that's fine. X squared times x plus 2 to the 28th power. Okay, so we're in a similar but somewhat different situation. We're going to make, so what seems like the only reasonable choice for you? That's maybe not a good question. What seems like a possible choice for you? What could I pick u equal to? Yeah, exactly. X plus 2. Now, we're picking u here. So usually we're trying to pick u that meets both criteria. We want u to have its derivative also showing up, and we want u to be kind of stuck somewhere. This one really, I mean, technically it is meeting both criteria. The derivative of x plus 2 is just 1, and so there's always a 1 that's in your integral, right? You can always have a multiple of 1. But really, this is only really kind of satisfying the other criteria, where the x plus 2 is stuck. We definitely don't want to let u equal x squared because its derivative 2x, we don't really have a 2x that's multiplying the dx, so that would be a not great choice. So we're going to let u equal x plus 2. Du is going to equal 1 times dx. So great. This is going to become then the integral of, well, my dx is du. My x plus 2 is going to be u to the 28th. And then x squared, we're going to have to do a back sub for. So u is x plus 2. That means u minus 2 is equal to x. So that x squared is going to become u minus 2 squared. And then we do need to multiply it out. So this is going to end up being, let's see, u minus 2 squared is u squared minus 4u plus 4 all times u to the 28th power. Then we have to distribute that u to the 28th to each of the terms. So that's going to be u to the integral of u to the 30th minus 4u to the 29th plus 4u to the 28th du. Then we integrate, we get u to the 31st over 31 minus 4u to the 30th divided by 30 plus 4u to the 29th divided by 29 plus c. And then finally, in the last step, we plug back in what u is equal to. So we end up getting, let's see, u is x plus 2. So we get a final answer of x plus 2 to the 31st over 31 minus, you could reduce 4/30ths to 2/15ths. 2/15ths x plus 2 to the 30th, and then plus 4x plus 2 to the 29th over 29 plus c. So the answer to the general question of should we always multiply it out is no, we shouldn't always multiply it out. The answer is we should multiply it out if it's like some quantity squared or cubed. But any higher power, they're not looking to have you multiply it out. They're looking to have you do probably a new substitution. A good question. Very illuminating for sure. All right, so that's the end of the first sample final exam on that handout. Let me go ahead and move to the second sample final exam. Get crazy. Let's open a new pack of pens. It's the last day of class. We deserve a new pack of pens. Always run that. Okay. I know, what a wild day. New pens. Who could have guessed? Along similar integration lines, if we have time, we'll be able to review a polynomial long division problem. Just mix it. Yeah, sure. In fact, no, this next one's not polynomial long division, but I'm pretty sure I had one here. Let me double check. I don't see one, but I think that's a good, I do feel like that's a good thing to do. Let me look real quick. I'm sure I know exactly where I can find one. 1 second. We can definitely, I think polynomial long division is definitely worth doing. So no care. Yeah. Where'd you go? There we are. Could be that. What's the point in here? I thought they were going to for better selection of problems. It could just make something up. The problem of making something up is it's always I remember I had a really good one a while ago. Anyway, we'll make something up. Will we really? Sure. This one's not my favorite, but we'll start with this, and then if you want more, another one. So let's do the integral x squared over x squared plus 6x plus 8. Which definitely is a polynomial long division problem because the degree on top is greater than or equal to the degree on the bottom. When they're equal degrees, it's a really easy long division. So I'm going to do x squared divided by x squared plus 6x plus 8. When we look at the highest power term and say, what do you multiply by x squared to get x squared? Well, the answer is 1. You multiply this by this. So you get x squared plus 6x plus 8. You subtract. X squared minus x squared is 0. And then nothing minus 6x is negative 6x. And nothing minus 8 is minus 8. Sometimes people, and I'm one of the people, usually people write the rest of the power terms like they write a 0x here and a 0 there to make it a little more sensible to be doing the subtraction. So then here's what we do. We rewrite the integral as the quotient plus the remainder divided by the divisor. So that's always the first kind of process you have when you have a rational function and the degree on top is greater than or equal to the degree on the bottom. You do the division, and then you replace the rational function with the quotient plus the remainder divided by the divisor. Okay, the quotient. Okay, yeah. So I mean, so yes. So then we still have to integrate the whole thing. So usually integrating the quotient is very straightforward. The quotient should just be nice integer powers of x squared, x to the first, 1, or 2x, right? Things like that. The remainder divided by the divisor is where we usually have to do a bit more work. So usually one of two things will happen for this leftover part here. It'll either be a u substitution, or it'll be partial fractions. I'm going to check for a u sub. If I let u equal the denominator, my du is going to be 2x plus 6. And if I multiply this by -3, I get -6x minus 18, which isn't that, so I'm out of luck. U substitution is not the way to go here. But the denominator does factor, which means I can probably definitely use partial fractions. So yeah, let's partial fractions it up. So -6x minus 8 divided by x squared plus 6x plus 8 factors as x plus 2 times x plus 4. And that's going to be equal to a over x plus 2 plus b over x plus 4. Then we multiply both sides by this common denominator. So we multiply both sides by x plus 2 times x plus 4. When you multiply this by that, the denominators cancel, and you get just -6x minus 8. When we distribute this to each of those, when you multiply this by that, the x plus 2's cancel, and you get a times x plus 4. When you multiply this by that term, the x plus 4's cancel, and you get b times x plus 2. And then in this particular instance, we're going to use the convenient values of x method, where we just pick values of x that make something 0. So we're going to pick x equal to -4. And on the left-hand side, -6 times -4 is 24. Minus 8 equals a times 0 plus b times -4 plus 2 is -2. 24 minus 8 is 16. 16 divided by -2 is going to be -8. So b is going to equal -8. And then we do the same thing, except we plug in x equal to -2. Plug in x equal to -2, we're going to get -6 times -2 is 12, minus 8 is 4 on the left. On the right, we're going to get a times -2 plus 4 is a times 2, and b times 0. So we're going to get a equal to 2. So now, this integral becomes the integral of 1 plus a over x plus 2 plus b over x plus 4. And then we integrate. Integral of 1 is x. Integral of 2 over x plus 2 is 2 natural log of the absolute value of x plus 2. Integral of -8 over x plus 4 is -8 times natural log of the absolute value of x plus 4 plus c. So that is typically what's going to happen when you have a polynomial division rational function. Is you're going to do the division, and then the leftover remainder over the original denominator most of the time is probably going to require partial fractions. But if you luck out, it might just be a u substitution. Yeah. see, where'd you go? I got hit on my new pens from this one. Let's go ahead and continue on with this. So here's another example. The integral of, here's another rational function. X to the fourth plus x cubed divided by 4x to the fifth plus 5x to the fourth plus 2. Now, if I was not being super careful about things, I might start trying to do partial fractions. But then I would quickly abandon that because I would notice that the denominator, at least the denominator, seems very, very challenging to factor. Right? I don't know typically how to factor a fifth degree polynomial unless it's very obvious. And it's not very obvious here, right? I can't factor like an x or an x squared out because of that plus 2 there. So it's probably not partial fractions because the denominator looks very challenging to factor and no one has told me how to do it. I guess I should have probably checked out the U substitution first. So can I let U equal the only thing that makes sense? The denominator. Well, of course I can. The question is it going to work out? Let's see what du is. Du is going to be 20x to the fourth plus 20x cubed dx. And yeah, I'm feeling good about that because I can divide both sides by 20. 1/20th du is equal to exactly my numerator, x to the fourth plus x cubed dx. So yeah, that's going to work out just fine. This is going to be the integral of 1/20th du divided by u. Or if you prefer, and I kind of do prefer, 1/20th the integral of 1 over u du. And these are literally the same, they're just written differently. I feel like this one's easier to mentally tackle. Like, oh yeah, I know the integral of 1 over u is just the natural log of the absolute value of u. For some reason, writing it like this makes it less clear, to me at least. That's 1/20th the natural log of the absolute value of u plus c. And that's going to be 1/20th the natural log of the absolute value of our u, which is 4x to the fifth plus 5x to the fourth plus 2 plus c. Okay. Move it along. Let's see what we got here. Find the slope of the line tangent to the graph. So slope of line tangent to the graph of e to the y plus the natural log of x squared plus y squared equal to 1 at the point 1, 0. So hopefully everyone sees this and immediately thinks implicit differentiation, right? This is screaming implicit differentiation. So what's the derivative of e to the y? Well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the y is going to be e to the y times y prime. I guess I should back up a little bit. When you're doing implicit differentiation, right, you want to take the derivative of the entire equation. So we're just differentiating both sides. Okay. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So the derivative of the natural log of x squared plus y squared is 1 over x squared plus y squared times the derivative of x squared plus y squared. The derivative of x squared is 2x. The derivative of y squared is 2y times y prime. Right? Or the derivative of some stuff squared is 2 times your stuff to the first power times the derivative of your stuff. Equals the derivative of 1, which is 0. Okay, now here's the thing. A lot of the time, if we're doing implicit, at this point we would solve for y prime. But they didn't ask us to solve for y prime. They asked us to find the slope of the line tangent to this equation at this point. So we do want to find y prime for this value of x and this value of y. So we might as well plug in x equal to 1 and y equal to 0 right now. So plugging in y equal to 0 and x equal to 1, I get e to the 0 times y prime plus 1 over 1 squared plus 0 squared times 2 times 1 plus 2 times 0 times y prime equal to 0. And look, this really simplifies down. E to the 0 is 1, so 1 times y prime is just y prime, plus 1 over 1 is 1. And then I've got a 2 here, plus 0 there. So I've got just 1 times 2 equals 0. So then y prime equals negative 2. So the slope of the line tangent to this at the point is negative 2. So specifically, if you're being asked to find the slope of a tangent line to some thing where you know you're going to have to use implicit, right after you take the derivative of both sides of the equation, that's when you want to substitute in the point that you're trying to find the tangent line, the slope of the tangent line at. Right? It's usually almost all the time going to be much easier than trying to actually solve this for y prime, keeping all the x's and y's in it, and then plugging in x and y at the end. So yeah, that's definitely a good thing to do. Let's see. Next one is trapezoid question. Not my favorite. Let's see. It's always hard. It's hard to keep track of the pens. Set up. Okay, fine. We'll do it. Set up the trapezoid rule estimate for the integral from 1 to 3 of e to the negative x squared dx with n equal to 5. Okay, we can do this. It's not terrible. If I'm doing trapezoid or Simpson's rule, typically to figure out what my points are, I like to just draw a little interval. So from 1 to 3, I'm breaking it up into 5 subsections. So my length of each subsection is going to be b minus a divided by n. 3 minus 1 over 5, which is 2/5. Or if you prefer a decimal, it is 0.4. So that means all my little sections here, 1, 2, right? That's going to be 1.4. That's going to be 1.8. It's going to be 2.2. That's going to be 2.6. Okay. So then for the trapezoid rule, the formula is b minus a over 2n times 1 times f of your first value plus 2 times f of your next value, all the way to, right, it's 2's the whole way, actually, and 2 times f of your next value plus all the way to your second, so your, not your last value, but your second to last value, plus 1 times f of your last value, where these values are just the endpoints of each of your subintervals. So in this particular example, our trapezoid method using 5 subintervals is going to be b minus a over 2 times n, which is 3 minus 1 over 2 times 5. And then it's going to be 1 times f of 1 plus 2 times f of 1.4 plus 2 times f of 1.8 plus 2 times f of 2.2 plus 2 times f of 2.6 plus 1 times f of 3. And that's kind of it. I mean, technically, okay, I suppose really I could probably simplify this a little bit. 3 minus 1 is 2, so 2 over 2 times 5 is going to be 1/5. And then I suppose if you were actually doing this on the test, you should probably actually write the function out, right? My function is e to the negative x squared. So I should really write this as e to the negative 1, because 1 squared is 1. And this is plus 2 times e to the negative 1.4 squared. And this is plus 2 times e to the negative 1.8 squared. And this is, I don't know why I'm putting the square on the outside of the parentheses. This is plus 2 times e to the negative 2.2 squared. And this is 2 times e to the negative 2.6 squared. And this is 1 times e to the negative 9, because 3 squared is 9. But that's it. That's all it wants to do. This one, unlike the one I did last class, we actually could talk about estimating the error in a reasonable way. So let's actually do that, because I do think it's reasonable to talk about that. So I want to ask the follow-up question. Yeah. How big does, that's not how you spell does. How big does n need to be so that our error is less than 1/1000? Okay. So the error formula for the trapezoid method is that the error is less than or equal to b minus a cubed over 12n squared times the maximum of the opposite value of the second derivative of x. Great. So then that's going to equal, let's see, b minus a is 2, so 2 cubed is 8 over 12n squared times, we have to figure out what the maximum is. Whatever that is, the maximum of the second derivative. And then that's going to be less than 1/1000. All right. So let's see here. The first derivative is going to be e to the negative x squared times negative 2x. And the second derivative is going to be, so it's going to be this times, so the derivative of this, which is e to the negative x squared times negative 2x times the other negative 2x, plus the derivative of this times this, which is going to be negative 2 times e to the negative x squared. And now check this out. We're going to factor out e to the negative x squared. So it's e to the negative x squared times 4x squared minus 2. And we want to make this product as large as possible. It might help to see that this is 4x squared minus 2 over e to the positive x squared. So to make this fraction as big as possible, you want to make the numerator as large as possible and the denominator as small as possible. So this is definitely going to be less than, so to make the numerator as big as possible, I'm going to let x equal 3. So it'd be 4 times 9 minus 2. And then to make the denominator as small as possible, I'm going to let x equal 1. So I'm going to get e to the 1. So this is less than 49 minus 2, so 34 over e. And this is where you would probably need a calculator at this point to actually do this problem. 34 divided by e is like 12.5. It's a little bit bigger than 12.5. So you can definitely say that this is less than, or yeah, sure, let's say 13. So then you pick a 13 there. It would have been nice if it was 12. And then you would solve for n. So, right, so you multiply both sides by 1,000, and you have 8 times 13 times 1,000 divided by 12 less than n squared. So then n would have to be bigger than the square root of 8 times 13 times 1,000. This kind of question typically requires some outside information where your teacher tells you some of the numbers or allows the use of the calculator. Or gives you an easier function where you're able to very easily see, oh yeah, the maximum of the second. Like, for example, just to kind of clarify, if your function was something like the integral from 3 to 6 of 1 over x minus 2 squared dx, then it's very easy to find the maximum value of this, of the second derivative, right? Because the first derivative is negative 2 times x minus 2 to the negative third. And the second derivative is positive 6 times x minus 2 to the negative fourth, which is 6 over x minus 2 to the fourth. And so then if you want to find the biggest this can be between 3 and 6, you want to make the denominator as small as possible. And to make the denominator as small as possible, you're going to pick the x value that's closest to 2, which is 3. So the maximum of the absolute value of f double prime on the interval where x is between 3 and 6 is going to be 6 over 3 minus 2 to the fourth, which is just 6. So sometimes it's much easier to see what the maximum of the second derivative is depending on the type of function. And so then this function, if you wanted to say how big does n need to be so that the trapezoid method gives you an error less than 1/1000, well, the error of the trapezoid method is going to be less than or equal to b minus a cubed over 12 times n squared times the maximum of the second derivative. You want that to be less than or equal to 1/1000. And that's much easier to solve this for n, right? We've got 6 minus 3 cubed, so 27. 6 divided by 12 just gives you division by 2. Less than or equal to 1 over 1,000. So multiply both sides by 1,000. Multiply both sides by n squared. So then n would be bigger than or equal to the square root of 13,500. So that's a much easier kind of problem to tackle because the function they gave you was a little bit nicer to deal with. Okay. Okay. What's next? Let f of x equal x squared plus 2x quantity times e to the negative x. Find the x values of all max and min points of f of x. Be sure to classify the points showing all work. Okay, so we want to essentially find and classify all critical values. So to find the critical values, we take our first derivative and we set it equal to 0. So let's see, I'm going to have to use the product rule. It's going to be the derivative of this times that plus this times the derivative of that, which is e to the negative x times negative 1. And I would probably start by factoring out e to the negative x. Oh, I am setting it equal to 0. Let's factor out e to the negative x. So if I factor out e to the negative x, I'm left with 2x plus 2. And here I'm left with a negative 1 times x squared plus 2x. So a negative x squared minus 2x. Let's simplify the insides here. Oh, that's actually pretty easy. The 2x and the negative 2x cancel out. So I'm left with e to the negative x times 2 minus x squared. So either e to the negative x equals 0. Wait, that never happens. E to the negative x, e to the anything is never 0. It's always positive. Or this equals 0. So if I set 2 minus x squared equal to 0, I'm going to get two different critical values. I'm going to get x equal to positive root 2 and negative root 2. And now we want to classify those critical values. And to classify them, we're going to use the first derivative test. So here's my first derivative sign chart. And you only want your critical values on the sign chart. You don't want anything else like 0, unless it's a critical value, which it's not in this problem. So I've got a positive root 2, and I've got a negative root 2. I'm just going to look in each of my intervals. Pick a number bigger than root 2, like 10. E to the negative 10 is positive. 2 minus 10 squared is negative. Positive times a negative is negative. So it's decreasing. Pick a number between negative root 2 and root 2, like 0. E to the 0 is positive. It's 1. 2 minus 0 squared is positive. Positive is positive is positive. It's increasing. Pick something smaller than negative root 2, like negative 5. E to the negative 5 is positive. 2 minus 5 squared is negative. Overall negative, decreasing. So we can say we have a relative minimum at x equal to negative root 2, we have a relative maximum, or you can say local if you prefer the word local, at x equal to positive root 2. And I think that's all the question's asking us to do. Yeah, that's it. Okay. Let's do the next one. Going a little bit back in time. So the next question says to find the derivative for f of x equal to 5 plus the natural log of x quantity squared divided by e to the cotangent of x. And I really think this problem is just, here's a gross derivative. Can you do it? So quotient rule. It's going to be the denominator times the derivative of the numerator. The derivative of the numerator is going to be 0 plus the derivative of the natural log of x squared is 2 times your stuff to the first power times the derivative of your stuff. Minus, switch it up. Now it's instead of the bottom times the top, it's the top. 5 plus the natural log of x quantity squared times the derivative of the bottom. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So it's e to the cotangent of x times negative cosecant squared x divided by the denominator squared. So e to the cotangent x quantity squared. And if they didn't say to simplify, I wouldn't simplify. If they did say to simplify, here's what I would really do. There's not a lot of simplifying to do here. So here's the, you can write this as, I guess you could factor out an e to the cotangent of x. So e to the cotangent x times, you have a 2 natural log of x times 1 over x. And here you have a minus, so a plus. 5 plus natural log of x quantity squared times cosecant squared x divided by e to the, when you have e to the cotangent x squared, it's e to the 2 cotangent x. So then you could cancel one of these with one of these and say it's just e to the cotangent x. Alternatively, which probably might have been a better choice, is we could have rewritten this as 5 plus the natural log of x squared times e to the negative cotangent of x. That prevents us from having to use the quotient rule, which probably is desirable here. So if I was doing this problem again, which I'm not, I would probably do it that way. If it's easy to bring your denominator up to the numerator, that's often a good choice. Really, if your denominator has like a single term, then I would say it's often worthwhile to rewrite your quotient as a product. But if the denominator was like x squared plus 2x plus 5, you don't want to bring that up as x squared plus 2x plus 5 all to the negative one. Not that you can't, I just find it to be less advantageous to do that. So for the next one, okay, yeah. Integral of negative 2x squared plus x plus 18 divided by x times x minus 3 squared. And right, as soon as we see this, we should hopefully all agree that the problem is really, really violently telling us to use what method of integration or what method of trying to integrate it. It's almost impossible to say it could be anything but partial fractions. And one of the kind of key things it's telling me is partial fractions is they've already factored the denominator for me. If someone has already factored the denominator for you, either it's partial fractions or they're being a jerk and they're trying to trick you and make you think it's partial fractions, which on a final exam is not usually the case. So this is a partial fractions problem, or at least I'm pretty sure it is. If you really wanted to check, I don't think we need to, but you could multiply out the bottom and see if it would be a u sub. It's not. If you multiply at the bottom, it's going to be x cubed minus 6x squared plus 9x. And the derivative of that definitely is not a multiple of that in any nice way. Yeah. I'm pretty sure it's not. Yeah, because that's going to be 3x squared minus 12x plus 9. And if you multiply this by 2, you definitely don't get that. Why did I pick 2? Because 9 times 2 is 18, but 2 times the other parts don't give you the other parts. So it doesn't work. Can't do the u sub here. Which we already were pretty sure about. And I would say if it's already factored for you, you really don't need to check. So what we do have, though, is this repeated linear factor thing. So we're going to say negative 2x squared plus x plus 18 divided by x times x minus 3 quantity squared is equal to a over x plus, you're going to have something over x minus 3 squared and all the lower powers. So we're going to have b over x minus 3 plus c over x minus 3 squared. It does not matter what order you do them in, as long as you get all of the lesser powers. So then we're going to multiply both sides by the common denominator. The left side, you always just get the numerator. Negative 2x squared plus x plus 18. The right side, depending on what you multiply by, various things cancel out. So when you multiply this by that, the x's cancel, and you get a times x minus 3 squared. When you multiply this by that, one of the x minus 3's cancel, and you get b times x minus 3. When you multiply this by that, both of the x minus 3's cancel, so you get c times x. And then we do our usual thing of picking convenient values of x. I will point out, whenever you have a factor that's to a higher power like this, you're always going to have to do something else because you're going to run out of sorry, brain. You're going to run out of convenient values. Wow. Okay, sorry about that. So x equal to 0 is one of them. 0 plus 18 equals a times 0 minus 3 squared is 9. And then b times 0 is c times 0. So you're going to get a equal to 2. And then x equal to 3 is the other convenient value that makes these things 0. When you plug in 3, you get negative 2 times 9, so negative 18, plus 3, plus 18. So the 18's cancel. Equal to a times 0 plus b times 0 plus c times 3. So c is going to equal 1. And now we've run out of convenient values. So this is where we then equate coefficients. And as usual, I like to pick the coefficient of x that has the highest power. The coefficient of x with the highest power. So I see x squared is the highest power I've got. On the left side, I have a negative 2x squared. On the right side, if you multiply this out, this would be x squared minus 6x plus 9. So you would have an a times x squared. And this would be b times x squared minus 3x. So you would have a b times x squared. But you would not have a c times x squared. So that means negative 2 equals a plus b. Since a is 2, b is going to be negative 4. Great. Now we can do our integral. So this is going to equal the integral of a over x plus b over x minus 3. And for any higher powers, I would really encourage you, instead of writing it as 1 over x minus 3 squared, I'm going to write it as 1 times x minus 3 to the negative second. Because it's easier to deal with that way. And then we integrate. The integral of 2 over x is 2 natural log of the opposite value of x. The integral of negative 4 over x minus 3 is minus 4 natural log of the opposite value of x minus 3. And the integral of x minus 3 to the negative second is x minus 3 to the negative first divided by negative 1. If you wanted to, you could totally rewrite that part as minus 1 over x minus 3. But I don't think you need to. We've got time. Let's do one more. Do one more improper one. So does the following integral converge or diverge? Integral from 2 to infinity of 1 over x times 2 plus natural log of x squared. So I have strong feelings about improper integrals and U substitution. My strong feeling is that you kind of don't want to mix them together. So I can see, hopefully you guys can see that this is going to be a U sub. Right? You're going to let u equal 2 plus natural log of x. Your du is going to be your 1 over x dx. So it's going to work out. But I don't want to have to change the limit integration. So what I'm going to do is I'm going to do the integration on the side. I'm going to do the indefinite integral. And I do recommend, like, if you have a question like this on a test, I do recommend showing this work. So show the work for the integration indefinitely. So that's going to be, u is going to be 2 plus natural log of x. Du is going to be 1 over x dx. So this is going to become the integral of, so 1 over x dx is my du, and that's going to be a 1 over u. The integral of 1 over u is the natural log of the absolute value of u. I don't really need the plus c. And then that's going to be the natural log of the absolute value of 2 plus natural log of x. Great. Now I can go over here and do the improper stuff. So that's going to be the limit as b goes to infinity of the integral from 2 to b of 1 over x times 2 plus the natural log of x squared. Oh, you know what? I made a mistake. I forgot the square here. That's going to change things quite a bit. That should actually be 1 over u squared. Sorry about that. Which means my integral, and that's the integral of u to the minus second, which is going to be u to the minus 1 over minus 1, which is negative 1 over u, which is negative 1 over the 2 plus natural log of x. It's very different than what we were about to write. So that's my integral of that. So then I'm just going to take this up and say, okay, this is equal to the limit as b goes to infinity. The antiderivative of 1 over x plus x times 2 plus natural log of x squared is negative 1 over 2 plus natural log of x, evaluated from 2 to b. Then we plug in our limits of integration. So it's still the limit as b goes to infinity of negative 1 over 2 plus natural log of b minus negative 1 over 2 plus natural log of 2. As b goes to infinity, the natural log of b also goes to infinity. So this denominator is getting infinitely large, which means this fraction is getting infinitesimally small, which means we're left with negative negative, so positive 1 over 2 plus natural log of 2. So this integral converges, and it converges to 1 over 2 plus natural log of 2.